Greetings to Succeeders. This is Professor Kaufman, and what ensues is a brief overview of what you're up against in Project 3. This will be our primary assembly coding debugging project for the semester, and after it, we'll leave x86-64 behind and return to C. But for the moment, you'll be up against both some coding and debugging that you'll need to do in assembly. The project structure is fairly similar to what Project 2 looked like, although sans the tree exercise that we did. There are just two problems. The first revisits the clock display problem that you did in the past project, and we'll have you recoding this clock business in assembly. And similarly, problem 2 is a very puzzle box-esque exercise. Rather, it's in binary, though, so Puzzlebin instead. As you survey the scene, you'll see as part of the code pack, which we'll download in just a minute, that there is a bunch of similarly named files to what you saw in Project 2. I'd recommend getting these anyway because they have a few slight tweaks to them that are appropriate to the assembly setting. But the primary source file that you will end up working on in that first problem is clock update asm.s. That's actually not part of the code pack release. You'll have to create it, and I can show you a quick and dirty way to how to do so. As well, you may want to transfer over your clock update.c from Project 2. If you were unable to finish that problem because the bit mangling sort of threw you for loops, we'll have a prescription for you to get a fast start in this case. As well, within the project files, there'll be a Puzzlebin. This is a binary executable, which is known to run on Grace and known to run on most Linux distros, though your mileage may vary if you're on like a WSL or something like that. But it's what will be the primary focus. Second problem of firing it up in GDB and working through it, along with then a input.txt file that you'll want to edit. There's a template version provided, but you'll heavily have to influence that with your own answers there. All right, let's get into it just a little bit. So problem 1 deals with this clock business. And if you recall from Project 2, you had 3 functions to write for that. There was a set TOD from ports, a set display from TOD, and a clock updates. Each of these in C was relatively short, but since we'll be hand recoding them in assembly, they're going to be somewhat more intense in that respect. There are some general prescriptions that I want to get out of the way with respect to hand coding things in assembly. But as you need a refresher on the problem domain, if anything we talk about is a little unfamiliar, then refer back to Project 2, as all of the prescriptions that are applied there are readily applicable here as well. There's a clock with a display, and you'll have to set this bit or set this little part of the LCD display properly. You have to deal with a struct and sort of put its fields that look like this and plop down an AM PM bit over here and so forth. So it can be good to refer back to that or to your solution in C for it should you have one. But keep in mind that each line of C code is 1 to 4 lines long in assembly, maybe even longer than that, depending on which kind of activity you're doing. Then you should expect that the girth of your assembly code is going to be somewhat greater than that. Just be sure that you take this exercise as one of hand coding that assembly code. If there's evidence that the code that you submit as your solution to this is not hand code, but rather machine generated, like, hey, I'll take my solution from Project 2, this clock update at C, run it through GCC, and just submit the assembly code that GCC spits out, then I will happily award that points to GCC, but 0 of it will go your way. There are some obvious things that we can look for in terms of hand-coded assembly, and I'll touch on those as we go through, and they generally sort of abide by the style that you want to follow here. But if you don't actually have a clock update.c file, then be aware of the following prescription, that staff are authorized to talk over your solution or lack thereof and what you struggled with on Project 2, and then show you the instructor solution to clock update.c there. And it is specifically written by me to make it easier to translate to assembly. So if you weren't satisfied because your solution to that meandered quite a bit, then feel free to hit up a staff member during office hours, either in person or Zoom based, to talk through, I really struggled with this clock update.c. I'd like to talk through what a good solution to translate to assembly looks like, and they'll be happy to do so with you. So by way of hand coding assembly, the following things will be things that we look for. Annotate your assembly. Have lots of comments. And this annotation comes in the form of both comments and things like label names that make sense, like .rounding up, because I'm rounding something up. The compiler will generate things like .l23 here. And so it becomes very easy to tell, like, if you've got all .l something labels for the label jump targets that you have, then it's probably coming from GCC and we won't give you any credit. And if you're looking to maybe convert some of those .l23s to labels that are more human interpretable, it is quite hard because GCC doesn't tell you exactly what it's doing. And the other hand-coded obvious sign is to make sure to use the division operation. GCC is full of tricks, and if it's a C bit of code that's dividing by 10 in order to get like what's the first ones digit or tens digit of this number, then GCC has some multiplication tricks you can use, and will use 6 or 9 assembly instructions to avoid the division instruction. Rather, you should directly utilize IDiv as it is the fastest, fastest clock time way to get the division done, but certainly the lowest number of instructions and most direct way to sort of interpret the C translations. Since GCC almost never uses division, if we can figure out a way around it, this will be a sure sign of hand-coded stuff there. So be advised there. You may wish to watch the following linked YouTube video on how to configure VS Code so that you have some assembly extension that allows you to do syntax highlighting and block common, uncommented code. It's put up by some sly YouTuber out there, and so it's not very long to set up. But we'll make things look more like, oh, here I've got an instruction and it's colored in some way, and to boot, the comments are colored in a certain way, and registers might be colored in a certain way, which makes it easier to read rather than being just sort of flat whites and so forth. There's several other cautions on here. For instance, common mistake, I forget to put a $sign in front of constants and instead use 0, which is the raw memory address 0, which will definitely segfault your code if you try to move something from that memory address. It's out of bounds. As well as a few other things like keeping in mind the registers, which registers to use, caller save preferred over callee save, but definitely ways to do that. And then a copy of the register diagram here that we studied in lecture that summarizes some of that information. Prefer to use blue registers. Know that arguments that come into functions, they come in certain registers over here. All that will be useful as you start to craft your own assembly. And I guess I should add one thing to this that might not be present, that there's an equivalent lab that studies similar things here. I believe it's lab 7 that deals with coins computation. There are a lot of techniques that are leveraged in that lab, and to some extent you could copy paste your way through it, but would be very fine and dandy to make use of here in this setting as well. Dealing with either a pointer to an argument that's a struct fielding to fill in, or a packed struct that's in there. All those were demonstrated in the lab and can now be put to use in this. All right, so what follows after that then is the basic structure of the file that you have to write for this, the source file clock update asm.s. In order to make any use of any of this stuff, I'm going to have to go grab the code pack to plop it down and make use of it. And then we'll copy paste and get started on this thing so we can at least run the test cases. To do that though, let's see, this is our section 3.4, so I can jump back there, but I'm going to jump back to the beginning here. Copy this link address and go use good old wget here to grab down the P3 code pack. Refresh. It's down over here, and I will unzip that. P3 code.zip. That'll create the P3 code directory, and you should see make files in there, Puzzlebin's in there, some testing files are in there, and so forth. There is, however, no clock update asm.s, nor a clock update.c file. Those are things that you can bring over from Project 2 if you like, or talk to a staff member. For now, though, let us create this clock update asm.s file. And here I'll just use the time-honored tradition of there's a template provided. And so I will grab this stuff here. Maybe come down to here, copy this thing, yank it in over here. And there will be a few changes to make here because this isn't compilable straight out of the gate, but this gives the basic overview of what's involved in that file. And I'll prefer to look at the text editor version I have here as the coloring scheme looks a little bit better. For instance, there are 3 functions to write. There's set TOD from ports, and there's a spot for that. It's in a text section, which is going to be executable stuff and marked as globally accessible. So any other code, such as the testing code or a main function, will be able to see this as it's linked to other things. Down here is a data section. We'll talk a little bit more about that later. And one of the common things to do is to lay out an array of stuff before use in there. And we'll see that. But that data directive right here, it changes this over to be read writable data. And it'll change back over to a text for the second function, this set display from TOD. That's down over here. Some techniques generated here that we'll talk about. And then the third section associated with clock update, the last function that you have to write. So again, this won't compile and run out of the gate. And if I were to try to do so, let's see, I'll come over here and I'll do a make, I think just a plain make up. We'll do that. I have to get into that directory. Hang on. There's P3 code, type make, and you'll get some complaints from the assembler. I'll make this wider. The C code that's provided as part of the infrastructure, the little main function that's provided, and the simulator, and some of the testing stuff, so forth, that's provided. But this clock update ASM that I wrote, you'll get assembler messages. This is the last part of the compiler, but to operate, to produce code, says there is no MoveX instruction. And oh yeah, there is no MoveX instruction. This is at line 9 up top on that. And that's because this is just a fill-in here to demonstrate a useful technique. If you recall, the first thing that this function is supposed to do, as you start reading things, is, oh, there's a global variable, clock time port. It's supposed to grab that global variable and then start doing analysis like, oh, if I divide by 16, then that's the number of seconds since the beginning of the day. And I can round that up or down based on the remainder for this thing and so forth. But just getting this global variable is, well, how do you do that in assembly? We'll talk about this in some more detail in lecture, but you've seen some examples of it if you track some of the lab and homework work already. The general technique is you first need to know how big is this variable and select an appropriate move instruction here. So go back and review. In the case of this clock time port, is it a short? Is it an int? Is it a long? And pick an appropriate size thing for it. So the name of the global variable will be here. And then the rip is an offset from it. Now, why that is exactly is something we'll, again, discuss in more detail in lecture, but it's actually sort of a long story and an interesting one for that matter. But with this syntax, you can then move that global variable into a register of choice. And of course, there's no reg over here. So you might pick something like RCX or something like that. Or if you thought it was a 32-bit move, then that'd be a move L of into ECX or something along those lines. And of course, change this global variable to the global variable you want to access. In this case, that'd be clock time port here. So that technique leads what we've been doing in lecture just a little bit, but is one that you can easily sort of make use of here, just to get that global variable into a register to start computing with it, shifting it, ANDing it, or dividing it, and so forth. The other things that we would want to do here to make this compilable, and since I'm not going to bother fixing this instruction entirely, I'm just going to comment it out there. Note the block comment part here, which is extremely useful to like, oh, I can block, comment, and uncomment things here. If your editor doesn't do that, get a better editor, or you learn how to do it within your editor here. There's a prescription, a reminder down here. Don't forget to return from functions, because if you start executing code here and there's no return at the end of the function, you just fall in this section and try to execute this stuff as though it were instructions, and it's not. So let me, before I forget, plop down a ret down here to return from this function. Generally speaking, that's all I need to make these complete functions. I'm going to take these again, which demonstrates some techniques to be useful to move some version. I'll pop down a ret down here, and then one more ret down here. And this should then remove the things that are not compile and add return instructions for each of the functions, so that the functions sort of run. They don't do anything. Like I come in and then I immediately return, don't set a return value or anything, but no matter on that. But this should put me in a position to be able to compile and run the tests if I've done everything right on that. So let me try and make here to build, and yeah, this thing built okay. And then I can type like make test prob1 and see. I'm going to run all 40 of those tests from the second project, and all of them fail because currently my assembly functions don't do anything. But that it puts you in a position to start writing bodies for each of these things to say, hey, in this first function, I got to set TOD from ports. I can move that global variable and do some stuff with it there. Okay, so that's a sort of fast start in terms of code over there. Now, as to what exactly you're supposed to do in each case for this, that's another matter. The essence of the first function is to populate this struct, which is passed in as a pointer and contains garbage as it's passed in, populate it with sane values based on an analysis of this global variable. So you divide it by 16 and you find, oh, it's been 60 seconds since the beginning of the day, so it's 12:01 a.m. And then you proceed to plop some things down, like, oh, it's only been 60 seconds to the beginning of the day. That means the time in seconds is 60, the minutes is 0, and the hours is, 12. Like, welcome to weird time stuff, because it's the 12 a.m. there. And it'd be in the a.m. at that point. Now, to get values into a struct like this in assembly, you have to know quite a bit about the struct layout. You have here a pointer to that struct. So it will behoove you to know, well, how does that appear in assembly? And if you've been tracking fairly carefully with things like, oh, there's this register diagram up here, you'll see one of the special purposes for the RDI register is that it is the first argument register. And so without doing anything in this top assembly code over here, as I come in to set TOD from ports, that first register, RDI, should already be set to be a pointer to some struct that I'm supposed to fill in. And wouldn't be bad to make a little note of that. It's like here, it's like RDI is a pointer to a TODT struct. And we'll make use of that pointer then to plop down values within those structs. Now, how do you get values into structs? Well, if it's a pointer, you're going to be using that little parenthesized like offset business. But you'd also need to know where things lay out. For that, you need a table, and I'll provide one over here. So for instance, if you were changing the TOD secs right here, the number of seconds since the beginning of the day, then you'd have to know where in the struct is that. Well, it's at a 0-byte offset. How big is this field? As declared up here, it's an integer, and so it's a 4-byte thing. And so if you had some register like RDI that was a pointer to that, then you could plop down a 5 into the day secs, by moving something to 0 off of wherever that register points. So 0 RDI in the case of the first one. If, however, you're trying to change the time secs over here, which is like within the current minute, how many seconds offset is it? Well, that's actually a short, so it's only a 2-byte. And you do well then to use a move W instead. And that field can't conflict with the first in the struct. Since this one was an integer and 4 bytes big, you have to move 4 bytes into the struct and an offset of 4 to it. So syntax like the following is appropriate for that. Take the 5 and move it not right where the pointer points, but 4 bytes offset from it. And here you can start to see, oh, that's why this kind of syntax is present in x86-64 to allow you to move something to a specific spot relative to where a pointer is pointing. And these offsets are often associated with the structs. Now, something has to determine, like, what are these offsets and why are they as such? But that's usually the compiler, and it was certainly so in this case. But then you need to know at the assembly level what is the compiler selected for that in order to be compatible with it. And tables like this are extraordinarily useful off of that. So generally, that's enough to sort of get you through the first function. If you combine it with a few other tidbits in here and things that we've been doing in lecture, that's you can access global variables using syntax that looks something like this. You may adjust the fields of the struct using syntax that looks like something like this. And then you have a bunch of addition, subtraction, conditionals in assembly that you'll make use of there. One proviso is that the division operation isn't actually used for this division by 16, because all of you know, if I have this number, this time of day or clock time port, if I wanted to divide by 16, I could shift by 4 bits instead, or look at the low 4 bits as that would reveal the remainder. And so you'll get an assembly equivalent of that as well here. Did it in C, now do it in assembly. Second function is somewhat more intense because it involves some bit level manipulations. Now, a careful observer will see the first argument to this was not a pointer to a TOD, but rather a actual TOD struct. And so within C code, you'd make use of some dots like TOD dot and TOD dot and so forth. This appears differently in assembly because this first argument register, which will be RDI, it's a so-called packed struct. So portions of the struct have been jammed into that register. And to access them individually, you'll need to do some shifting and some ANDing. GCC makes some decisions about this, and it's pretty good about then selecting, oh, actually I can't fit this struct, which has, where was it? Up here, it has 4 plus 2 plus 2, so that's 8 bytes plus 3 more bytes. So it's a total of 11 bytes for the struct. That doesn't actually fit into a single 64-bit register because they're only 8 bytes big. So it'll actually pack this struct across 2 registers. And so the first 2 argument registers, RDI and RSI, are used for this struct. And as you'd want to access its fields, you have to do things like, oh, let me fish this time sex out of the RDI register. I'll have to shift that register over by 32 bits because the first 30 bits are this first struct field over here. And then perhaps do some masking, like AND it with some ones in order to make sure that whatever register I've got this thing in, that's the only thing it contains is this 1 bit over here. If you didn't know, the C compiler will do this for you as it generates assembly code, and it makes you appreciate GCC a lot more when you have to do it by hand like this. So despite this thing only taking 2 arguments, you'll see that it uses 3 registers because 2 of them are used for the structs, and the third one is where this display pointer will be at. After you get some of the struct fields sort of sorted out, you'll use a similar techniques as to what you used in Project 2 to say, I'm going to use division, determine that for the minutes, the ones digit of it is a 5, and the tens digit of it is a 2, because it's something 25, like 1025. And so I'll need to put on the display screen a bit pattern that's associated with a 5 and a bit pattern that's associated with a 2, shift it over just a little ways. That ends up being very similar to what it looks like in C, except that if you're looking to lay out an array that has your bit patterns in it, you have to use a slightly different technique for it. One example of that is here to lay out a section that's a data section. You could also write just data. And some more examples of it appear in this middle portion of the code template, that if you had a single number that you wanted, like my int, then you can declare that as a label, this spot in the code / data, wherever it is, in this data section in this case, and plop down 4 bytes there that represent 1,234. If you want an array of those things, it's a matter of give the array a name and then plop down successive integers or shorts or longs over here. And the syntax for constants over here that's supported is identical to GCC, so you can use plain integers, you can use hexadecimal, or you can use binary constants. Most of you will probably prefer this last one as to lay out the bit patterns that are appropriate to display those digits. Most of you used binary for it. So here in this middle data section, then that's where you can plop down an array to make use of the fact that, oh, on the 0 spot, I can put down a bit pattern that shows 0. And in the 1 spot, I can put down a bit pattern that would show a 1 if I got it in the right spot in this image. Now, how do you access that array? Well, it's now a global variable that's accessible from within this assembly file. And there are a couple of techniques over here that demonstrate that. For instance, if I was just trying to get my int, this 1, 2, 3, 4, into a register, similar syntax to what we used above with the global variables up here applies. So my int, that's the global variable name, an offset from the RIP, and since it's an integer, move that into EAX over here. You could also use a leak to say, I don't want the value that's stored at my array, I rather want the address at which it's stored at. That load effective address here, always with a Q for actual addresses, load that address, the starting address for my array, into the register RDX over here. So that set of techniques then will be useful to you as you'd want to make use of an array that you have over here. But aside from that, follow a pattern that you laid out in your C code to do some division and figure out here's ones digits, tens digits, ones digits, tens digits, and then establish some place where you're going to start laying down bit patterns, shifting and ORing and so forth to construct that in its whole. Just don't forget by the end that you will need to set this second, it's actually the third argument register display over here, set that to be whatever value that you decided upon for the overall bit pattern that shows the digit array there. The final function is short and sweet, but involves one final twist on things, wherein this clock update is supposed to call the previous two functions, capture the return values, and in order to provide those functions with the right environment, you need to use some local variables. So generally, you'll have seen in labs, if you've tracked with those, that you can lay out some space in the stack by using either a push instruction or a sub instruction, manipulate the stack pointer. This will create local space. But there are several different constraints on this. For instance, whenever you'd call a function down here, then the stack pointer needs to be divisible by 16, aligned properly. And irritatingly, if you don't align it to a 16-byte boundary, your code will run fine on some machines, a la Grace, but then break with general protection faults or some such on other machines like Gradescope. So this one's a tricky one to get right, and you'll want to follow the approach demonstrated in labs fairly carefully so that you stay on the right side of this one and don't get bitten by a bunch of non-compiling code or non-functional code on Gradescope. So make sure to test there. So one setup like this to create some local variables and line up the stack allows for several function calls to happen later. Just make sure to undo those changes. If you pushed, then pop. If you subtracted, then add on to shrink the stack to a higher address, and so forth. We'll cover those things in more detail in lecture, and you've got some demos and labs of that, so make use of those things as they come up to resolve this part. This will give you a chance then to see very directly, write your own codes, like how does a bit of C code establish a local variable? And it's usually just, lower the stack pointer. Now this space is that local variable. You can put things there, or if you have functions that are supposed to fill in what the values are by address, then load up the address and have the function do it for you. That is the essence of this first problem with grading criteria down here. About half the credit is for automated tests, but there's substantially more here for a manual inspection where someone will get some eyes on the different aspects of the handwritten assembly code. There's quite a few style points here, about 10 in this case. And so make sure to comment your code, make comments about what registers are used for at various spots, or suffer the consequences of not that. There isn't a ton of indentation associated with assembly, but reasonable indentation so that instructions are offset from labels is much appreciated. And then along with some specific criteria to demonstrate techniques that are used here. One nice side bonus is that if you tallied up all of these points, you'd find, there's the grading is supposed to be out of 60 points for this, but there's actually 65 available, so you can earn some makeup credit just by fulfilling all of these constraints here. So enough of problem one, let's go to problem two, which is even more devilish. So you'll be using heavily the debugger in this case, and so there's a link again to the debugging guide that we have, as well as a specific link to dealing with assembly there. And I'll demonstrate a few of those techniques here because what's at stake is this Puzzlebin executable. There's no source code associated with this thing. And so you have to learn how to get GDB to show you what it can about the underlying structure of the program, mainly in assembly there. The general flow will be fire up Puzzlebin, set the arguments to whatever input.txt file is like. That should feel familiar because it's exactly what you did with the puzzle box that preceded it here. And the first thing in there will be your user ID, so that creates some randomization. Your solutions to this in input.txt won't look exactly like your neighbors. So allows you to collaborate. Just know that you won't necessarily have the exact same answers. Within that input file, it's generally one answer per sort of, here's this phase, here's an answer for it per line, and so forth. And we'll have sort of supplemental things in there. The debugger will put it into assembly mode, so it actually shows the disassembled instructions, because that's all that's available from this thing. You set some breakpoints, you perhaps show the registers, you run, and then start looking at how things change as you go through. And I'll take you through more or less the first phase here in our sort of input there. Now, by popular demand, both amongst students and TAs, there is a little bit of a pressure relief valve here. So if you really get stuck on like phase 3, you can enter the input skip, all caps there, And for a very minor penalty, it'll bypass that phase and go to the next phase. And that's hoping that you will come back and revisit that phase in order to actually get an answer to it and avoid the penalty there. And skipping all phases leads to a negative score, like -7 out of 40 or something. So don't skip all phases. That's just silly. Also, in the process of unzipping, because we're sending you a binary, it's possible some of you will get this little permission denied error. It just means the binary doesn't have the execute permission set to it. You can fix that by running this command yourself or just typing make, and it will automatically update Puzzlebin to have that. And after that, you should be able to run it as a program on your system of choice. So just be aware of that part. So before we get into the actual debugging, keep in mind the following, that you don't have to finish the entire thing, that finishing phases 1 through 6 will get credit, full credit, full 40 points. If you finish phase 7, then that's 10 makeup credit for you. And hidden amidst the business that is the Puzzlebin, there is a bit of a secret that can earn you 10 additional makeup credit points. So a max of 60 on this one. And so if you're looking to make up some ground on a flubbed project in the past, then this would be a good time to invest some of your effort, as you can get some rewards there. Although getting this last one is a bit tricky, both finding it and then resolving it there. So let's take a quick tour here so you understand like this isn't that bad to get through. Let me jump over here, and rather than use the janky shell that Emacs provides, I'm going to fire up a proper Xterm editor, the GNOME terminal. That's my platform of choice over here. So this one will look a little bit more normal. GB tends to behave badly under Emacs because Emacs has its own way of doing GB stuff, but no matter there. So in here, there is a Puzzlebin. And the typical sort of dev cycle is going to be to fire this up in GDB, but also then somewhere over here to keep your input.txt up. And so over here, I'm going to pick a semi-random, I'll pick prof k. That's it. And there's a bit of a hint that the first input over here, there's some wordage associated with it. And so I'll leave this as is for right now. But this is my unique ID, and so will give me my sort of unique experience, just as it did for Puzzlebox. Now, starting GDB over here, TUI on Puzzlebin, you'll be confronted immediately after pressing enter a few times with the no source available. And this is fully intended. There is nothing you can do but to get said source code, so don't try. Instead, recognize that GDB is actually dealing with a binary, and so is well aware of a lot of conventions associated with it, and invoke the following command, layout ASM, which will show you the disassembled binary, and this is translated back from the binary into a textual form of the assembly over here. Now, there'll be a few differences that are cosmetic, and I think even in today's lecture we talked about this. Different tools take different conventions on it. You'll notice, oh, there's a subtraction and a movement and a LEA, load effects of address. None of these have suffixes. There's no push Q or push L or sub W, etc. Instead, you can infer what the operation size is based on registers. This is pushing a 64-bit register, so it's probably a push Q. This is moving a 32-bit register EDI into another 32-bit register, so it's probably a move L. And that difference between what you'd write as your coding out assembly and subject to the whims of the assembler, that's one tool, versus what you'd read here, you're subject to the whims of GDB and how it disassembles things. It's slightly different. Those are two different tools written by two different people, and they didn't necessarily talk a ton to each other about agreeing on that stuff, but shouldn't throw you too badly. The main point is you have a window here that shows you, this is source code in main and so forth. And there's phase code up here for that kind of stuff. And so we'll set some breakpoints in a second to deal with this. Now, it's a bit limiting to have this is all I can see of the source code. So the entrepreneuring debugger here will recognize it'd be nice if I could have this in a text file someplace. Perhaps there's a way to get GDB to do this, but we talked just today in lecture about another binary tool that's used for this. And I can't remember if I had mentioned this in the spec or not. I should add it if not. Say on here, did I mention object dump? Yeah, the object dump utility here is meant to deal with binaries and do certain things like disassemble them. And so a good idea for a lot of you is just to straight up invoke that. Here, object dump dash D for short for disassemble. And there are a bunch of other functionalities encoded in object dump. You can read the manual about it. Here's a Puzzlebin. This will dump the disassembled version onto the screen, and you can see this is flying by pretty fast. And I don't care to look and wait to the end of this. I'm going to Control C this, the keystroke, which will stop a program running, and instead make use of a common Unix trick that we'll talk about later, and redirect that output from the screen into a file. And we'll actually implement versions of this later on in programs when we get into our unit on Unix stuff. So I'm going to call this puzzlebin asm.s to indicate it's not exactly hand-coded, but it's pretty close. Notice that goes a lot faster. And if I look around in the directory now, there's a new file in town. It's clock update asm.s. What was getting dumped to the screen is now in here, and I can, let's see. Oh, no, not that one. Clock update. I said Puzzlebin asm.s. Sorry there. So this is the output of that object dump utility, and it's rather long and verbose, but extremely useful. For instance, I can poke around here and see, is there a main? And you'll see reference to it, but here's right where main starts. And so if I come back over to the GDB window here and scroll back down to where I was at, you'll see very identical instructions, push RBP, push RBX, subtract 8 off the stack pointer. That's exactly what I see over here in text. So this is a more convenient way to potentially view that source code. It shows the actual bits of the instructions if you're curious about it. But if you need to take notes about what you think is happening at each stage, like that's a convenient spot to do so over here. So that's all I'll say about this bit over here. Now, obviously, the main action for this is going to happen in the phases. And so let me start out, as you probably did with Puzzlebox, and set a breakpoint at phase. I'll ask for tab completion here. They all start with 0. I have my choice of 1, 2, 3, 4, 5, 6, 7. I'm going to choose 1 because that's an obvious spot. So breakpoint's been set. I'll maybe want to set my args to be that inputs.txt file, and then I'm going to give it a run. So the screen has become mangled, as it's wont to do. There's some output here that would normally print to the terminal on the screen. As prof k, I get a certain hash value. Some output here about the first phase, but my breakpoint hits here, and that's now I'm within the phase 1 code. I'm going to punch the keystroke Control L to redraw, so that's the janky interface here looks slightly sane here. And I'm at this first instruction in phase 1. Now, I scrolled up just a little bit to show, like, the first instruction of phase 1, there's literally no separation for it from the last instruction that is in the preceding function up here, handle signals. And if you scroll down a little ways, there's a last instruction here in phase 1, and then immediately after that is the first instruction in the function phase 2. That's because once you pack this stuff into binary, like, it's all just glommed together. There's a series of bytes over here that are instructions. And the general expectation is that if, I got to this point in phase 1, I'll call this function and never return from it or something like that. And so I can start immediately with, here's where the bytes for phase 2 happen. It feels unnerving to have all this stuff packed so closely together, but it's exactly the field that the processor operates in. My breakpoint is set here, and you'll want to learn just a little bit about stepping and so forth in instructions. If you just step here, then things could go awry a little bit because the debuggers can try to guess how many lines of assembly correspond to stepping one C source line forwards. Well, what I really want to do is step a single instruction forward, so step I is more appropriate. So you'll see over here, I do a few things like step, step, step. A lot of what's happening here is happening in the register file. And in this case, I stepped into this next line function, which I don't really care to sort of go through. So I might type like finish here to finish up with that there. And you might as well use the next instruction, ni, which will step over function calls like this. Since a lot of the action is in registers, it'd be useful to have those around. So let me change the layout here to regis. and I'll see at least some of the registers in my limited window here. If you decrease the font size, you can start to see more of the 16 general purpose registers in x84. And if you step out even further, then you see special purpose registers like the RIP and the flags register. I don't think I need those right now, so I'm going to reduce this to just deal with like the first 8 registers because that's all I think I need to see right now for this example. And so as you'd see, like, oh, I'm going to move REX to RDI. If I do a next instruction here, then up here, I guess it didn't actually change because they must have been the same or something like that. But if I execute this next instruction of move, like whatever this thing is, then I should see RSI has now changed up here. I'm about to call a function, call this thing, and in some cases the debugger knows like, oh, there's a function at this address. It's called strcompb. And strcomp hopefully is familiar to you at this point. It's how 2 strings are compared. You can, if you wish, step through that function. But in my case, I would probably just do an NI, a next instruction, because I want to see what's the result. As we've seen in lecture and alluded to, that functions return their return value in the EAX register if it's an int, or REX register if it's a pointer, things along those lines. And this is not meant to be confusing. strcomp PB is actually just a pseudonym for strcomp, and it's there. So this is probably comparing a couple strings, and we'll talk about what strings it's comparing in just a second. But here, there's a test instruction, and it's testing EAX. Since this is right after a function call, I know EAX was set by this function call. It's the return value for it. If I look up, that's a big number. It is definitely not 0, which is the value that this function would return, what strcomps generally return if 2 strings are equal to each other. Well, that's cool. That's interesting. So we'll test on that. And we talked today in lecture about, oh, that's oftentimes testing for zeroiness out there. And if I do some next instructions here, you see, oh, there's a test followed by a conditional jump. And this is jumping if the past test that was done indicates 2 things were not equal. This was definitely like a not equal, not 0. And so I'm about to jump to what will become a familiar sort of rendition, is a setup and then a call to the failure function. Now I may as well to just step through this. I'll call NI, which will execute this entire function and put some things on the screen here. And I'll do so because this part is, I think useful, and a lot of students skip it. These messages about failures can sometimes reveal hints, so they're worth looking at here to see that. Yes, I am failing, but there might be a bit of information you might glean here. For instance, the failure message. In this case, this is not the quote you're looking for. Not move along. If you catch that reference, it's a bit obscure, but no matter there. So there's something involving quotes over here. And to gain further insight, I'm just going to blunt, try a rerun over here. This will get me back into main, and the intrepid observer will see, there is some mention of a quote over here. And it would be useful to know something about what this thing is. There are a couple ways to go about that. You might try and figure out, hey, how do I examine what's at this memory address over here? Or you could be lazy and just execute a couple lines over here. And for instance, realize, oh, if this next line function, as it's called, it's returned something in REX over there, then I could actually look at what REX is. For instance, let me print out what REX is. Not particularly useful because, like, okay, it's some 140 trillion 737 million, whatever number that is. But if you're sort of concerned, like, why would I want that number? You might look over here and say, in hex, this looks suspiciously like maybe a memory address here. It's got like the whole 7FF like stack-based thing over here. So instead, you might examine what's at that memory address instead. As we've talked about before, there's a separate command for this, the X command in GDB. And so examining what's pointed at by REX over here, that doesn't give a ton of insight either, because it's something involving inputs plus 128 and some crap there. But you also have to keep in mind, just like registers up here don't reveal what kind of data am I? Am I a decimal number? Am I a pointer to something? Am I something else for that matter? The GDB is not equipped here to figure out like what exactly is at here. So some pot shots are in order. Examine this as a decimal number, and that's not. reviewing other common data, I examine it as a string, and how now, brown cow? This is where the input's coming in. And the call you'll find next input line is what reads input from your text file and plops it down someplace that's usable, for instance, the return register over here. And so this is a sort of common paradigm. It's like, oh yeah, I want to check my input to see like what it is and where it's stored. It's going to move over into RDI here as we move one instruction forwards there. Now this next bit, I'd like to know about this quote. And since we're about to do a string comparison with something to this thing, you might sort of surmise this is probably some string. Again, the easy way to get access to this is just execute the instruction, because at this stage, RSI changes to value, and that also looks like a memory address. And since I think I'm dealing with strings, let's examine what's in RSI as a memory address. And down here, we see something that looks like a quote. And if you don't know this one, then go see a movie. There's been a couple of them where this one comes out now. But the intrepid observer will now start to understand, okay, if we're going to compare these things and I jump to failure if they weren't equal, maybe I want them to be equal. So I'm going to come over here to that input.txt and start typing. I must not fear, period. Fear is the mind killer. Thank you, Paul. Okay, so I'll save that, and the saving is important because otherwise, that's a changed input, so I'll have to rerun the debugger at this stage. Give that a rerun here, refresh, and now I'm going to start doing some nexting here to move forwards. I've gotten that loaded up, so let me just check here. I'm going to examine what's in RSI. Is I must not fear, fear is the mind killer. Examine what's in RDI. I must not fear, fear is the mind killer. Why those two registers? Well, if you were tracking, they're the first two argument registers. First argument, second arguments. And they're getting passed in a stir comp, so it's probably two strings that need to compared. One more NI to step forwards, and you'll note now EAX was set by the function call, and it's 0, which probably means I'm in business. So I'll take another next instruction, say jump if this EAX against self was not equal. It is 0, so I'm going to get out of this function and get me some points at this stage. You'll see over here, there's a score variable up in main and some points and so forth. And if I move forwards, I can now examine, like, what is my score? Examine, maybe as a decimal integer score. Let's see, it doesn't know. Say, oh, it has to, okay. I'll cast it as an int. Examine is it. Can I, exact, right? Okay. Print. Oh, print the score. There it is. Okay. So I've got 5 points. Now, if I were to bug out for just a second, and handy keystroke to know, Control Z will suspend the debugger, and FG will bring it back to the foreground. So handy to know about. So I'll suspend and then run Puzzlebin here with input.txt. Then you'll see, hey, I've got 5 out of 40 points here, which is a good start. And I don't have any input for the next phase, so that'd be the next sort of step along the ways, is to plop down some inputs and then see, does it match appropriateness, match the format that's expected. I will caution everyone that not every phase expects string input. So you might expect numbers here, you might expect other things as you go forwards. And so a good first step in the next phase, and I can jump back over here, maybe set a breakpoint in phase 02, and delete my first breakpoint so that as I run now, I'll land at the beginning of phase 2 over here. A good thing to sort out is, what is the format that is required for this phase? Early on, you have to figure out, am I giving letters, numbers, whole strings, just single words, etc. There's a common function that's used. It's the scanf function over here. Learn about it, learn what its arguments are, and if you're able to examine those arguments, you'll be in business to at least quickly determine this is what the input format that's expected, whether it's numbers or strings or something else for that. So spend a little time figuring that part out. All right, I think that's enough for the moment on this, at least enough to get folks started. Again, these two problems are independent, so you can work on them concurrently, sort of flipping back and forth, or try to get all one done and then do all of the other, and so forth. This is a harder exercise than Puzzlebox was, but it will teach you much about the kinds of code that the compiler generates for assembly, and perhaps give you a bit of inspiration as to what kinds of assembly code you might write in your own versions over there. That's enough for me. I'm out. I'll see you in lecture on Thursday, and happy hacking as ever.